You're in the review session if you don't know where you are for 2A. In a moment, I'm going to ask you if you have any topics that you'd like me to cover, and I'll write them down. And in about the hour we have, we'll see how much I can cover. And then I'll dismiss the disgruntled students. And anybody who has specific questions left over afterwards, we'll work on those. If all the technology works out right, sometime today, if not tomorrow, I'll have this review uploaded if for some reason you want to watch it again. As always, I have my YouTube videos. This is the site if you need to find them. And then it's kind of, I don't know, probably too late, but a bunch of people have asked me if I'm going to have readers. I'm not teaching 2B, but if I'll have 2B readers. So, because enough people ask me, I've been preparing them, and I should have them in Davis Copy Max by next week. So, if that's interesting to you. Okay, cool. So I am ready. What topics do you want me to cover? Raise your hand. Yes? Hybridization. That's over here. Yes? Hydrate, that's random. Yes? Lewis structure. Yes?
Polarity.
Yes?
Ionic.
Yes? 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 Electron conveys? No, wait, that's not okay. Yes? Limiting reagents? Yes, what of you two? What's that? Quantum numbers? Yes? Yes? Okay. What of you two over there? Partial pressure? Yes? Percent composition. Okay, just a couple more. Yes? Shielding. Way in the back.
Wave functions.
Wave functions. Okay? 3 more. Yes? CO3? CL3? Z effect? Yes? Shapes of orbitals? Oh no, of Vesper? Okay, yeah. Okay, one last one. Yes? Redox. All right, it's impossible to cover this in an hour. Oh gosh. Do you want to start it on the right-hand side or the left? Right. Raise your hand. Left. Right. I'm going to go this way. determined by the groups. So you want to be able to know this depending on the groups. Okay, so given any molecule, something like that, you want to tell me the hybridization. And so of any given atom, I would tell you. So for example, let's look right here. You just count groups. How many groups? Not one. You should count two, because there's a carbon here, and every carbon has two bonds. So two groups, sp. That one's sp. Two groups, a triple bond and a single bond. Oh, here. How many groups? Two. A single bond and a triple bond, sp. How about here? You should see three groups, sp2. Right here. You should see four groups. Let me erase this a little bit. Every carbon has four bonds. So a total of four. So this is sp3. Okay? How about there? How many groups? You should see four. Every carbon has four bonds. So it's three undrawn hydrogens, and then the fourth single bond, sp3. In general, things with single bonds are going to be sp3. Things with double bonds will be sp2, and things with triple bonds will be sp. Okay? That's about it with hybridization. I'm trying to think if there's anything else. You can do overlapping bonds. That's the other common question. So we can say, let's do a different color here. Let's take this bond right there. And we could ask you, what orbitals overlap to make that bond? Okay, what orbitals overlap to make that bond? Well, there's a carbon on the left and the carbon on the right. So this is first a sigma or a pi bond? It's a sigma. All the single bonds are only sigma bonds. So it's a sigma bond with the carbon on the left having an sp2 hybridized orbital, overlapping with the carbon on the right having an sp hybridized orbital. Okay? So given any particular bond, you should just be able to write or identify what orbitals are overlapping. That's about all I've got for hybridization. As long as you can count the groups, you're pretty good. Any other questions? Maybe when we do some Lewis, you'll see it, something else. Yes? What's that? For the triple bond, okay, I'll do this and then I'll move on. Okay, for the triple bond, there's three bonds. What kind of bonds are there? A sigma and two pi's. So there's three bonds. For, and this, it seems like a lot, but it's actually pretty simple. The two carbons form a sigma bond with the hybridized orbitals. The carbon on the left with the sp overlapping with the carbon on the right with sp. Notice they both have sps. Okay. Pi bonds, or the double and triple, the second and the third bond, are always from 2p, as far as our class is concerned, always unhybridized 2p orbitals. So the second and the third bond, which are just pi bonds, are 2p unhybridized orbitals. Okay? All right, I think I need to move on from there because we have no time. MO diagrams. And those next. Okay, for MO diagrams, does somebody want to pick me a molecule? We did for in class. And two, we're not done. What charge do you want? You have seconds. So you can put a -1, a +1, a +1. There we go. Oh, are there, who's here not from my class? Wait. Okay, my class feels cool, apparently. Just one slight note. Some instructors differ on what to write in the atomic orbitals. Okay, the molecular orbital is always the same, but what I'm describing is what I think is normal and what my class should be writing. But there's a slight difference. Sometimes people, even though this is a plus, will put two neutrals here. But N and N plus come together for overall charge of +1. Okay, just FYI. All right, so otherwise you just need the core orbitals, electrons in orbitals, so, or the valence. So this is a 2s and 2 p's. Okay, I would write the electron configuration. For nitrogen on the left, it's 1s2, 2s2, 2p. Hey, whoever asked me electron configs, we're doing it right now. 2p3. And this is 1s2, 2s2, 2p2. And it's a +1 charge. So that's going to tell me later how many electrons to put in. Okay, so every bond has two parts, the antibonding and the bonding. So a low energy and a high energy. Like that. And then for the upper picture, now I'm thinking, okay, it's a nitrogen. Remember, nitrogen in lower in atomic number has a different P structure than oxygen and above in atomic number. Because of that, I would need to remember that it's 2, 1, 2, 1. Okay, so you need to know this template. Okay. How do you know? Because it's nitrogen. Nitrogen and below, 2, 1, 2, 1. Oxygen above, 1, 2, 2, 1. Yeah, it's on my reader, on page, whatever, 103-ish or so. This is nitrogen and below, 2, 1, 2, 1. On page 104, oxygen above, 1, 2, 2, 1. Okay, so now you have to name them. Sigma 2s, the subscript is from the atomic orbitals from. The superscript is if a star if it's above, and an unstar if it's below, star meaning antibonding. If there's two lines, it's a pi, pi 2p. One line is sigma, sigma 2p. Two lines of pi, pi 2p. One line is sigma, sigma 2p. So it's stars are up top, that are asterisk, superscripted. And there we go, there's the names of all of them. And now, lastly, we fill in the electrons. So on the left-hand side, it's 2s2, 2p3. And on the right side, it's 2s2, 2p2. So 2p2 is the 2 electrons in the p. And then for the bottom, 2 electrons on each side are a total of 4. So fill in this, 1, 2, 3, 4. For the top, 3 electrons on the left, 2 on the right, total of 5. If you don't know how to fill it in, you can watch my pen. 1, and then 2 goes here unpaired. 3 goes here paired. 4 goes there, and then now 5 going up to the next one. Okay? That's the MO diagram. We're already done. The next 2 parts that are typically asked have to do with magnetism bond order. So for magnetism, anybody, what's magnetism of this? You would say para, and the reason is there's an unpaired electron in the center. Okay? In that case, just because of that, it's paramagnetic. Okay? And then the bond order. Okay, it's something minus something divided by 2. What's the first something? Yeah, the first something has to do with electrons in bonding molecular orbitals. 5. What's the second something? It's going to be 0. It has to do with the number of electrons in anti-bonding molecular orbitals. There's 0 up there. So 5 minus 0 divided by 2. This is a 2.5 bond. A bond order of 2.5. Did I miscalculate? No? Oh, yes?
Isn't there antibonding in the sigma 2s?
There is. Somebody's asking about antibody in the sigma 2s. That's right. You can use these to calculate the bond order if you want, but you don't need to. When I calculate the bond order, I only do it for the uppermost diagram. But if you wanted to, you could add 2 to that and 2 to that, you get the same answer. Okay? All right. And there's also a 1s too. I'm ignoring all those that are totally full. Okay, Bill. All right. Any questions on MO diagrams? That's it. Just make sure you can fill it up. You'll be good. Yes? What's that?
On one of the practice tests in the answer key, it was like O2 minus, and they didn't put the electrons in the 2p before we were on the sides.
Yeah, that's what I'm saying. So one of the practice tests was O2 minus, and they put neutrals, I believe, here. That's because I didn't make that key. I contributed to the test, but I really, don't totally care, but I think it's appropriate to put minus charge. You need to check with your instructor about what your instructor thinks should be here. Okay, cool. And believe it, I think Igor has a review session today, right?
Yep.
4:30?
No, it's 9 to 2.
9 to 2. That sounds crazy, but if he does, that's cool for him. Big. I thought it was like 4 or something. Okay, cool. I think 9 to 2, there's a chemistry review, like with TAs. Okay, what was next? Let's do Luke. We're going to knock all of these out. All of us. All chapter 9 right now. Okay. Let's do this Lewis structure. And I'm telling you ahead of time it's V-shaped. It's shaped like a V. Okay? Alright, let's try it. Valence electrons. There's 5 iodines in column 7 plus a -1 charge. That's 35, 36. So now I could put them all in a clump, but that wouldn't get me towards a V-looking shape. Okay, remember what V's look like, that letter right there. Okay? So it has to be in a line, according to what they told me. Let's put the lone pair on. So first I draw the skeleton, that's how I always start. 2, 4, 6, 8 of 36 electrons used just to draw the skeleton. Now let's do the lone pairs. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So remember, I do the outermost first, 20 of 36. Now let's do the inside. Let's see, 20, 22, 24, 26, 28, 30, 32 of 36. I have 4 more electrons to go. Where do they go? You want to put them on, there's 3 center ones. Which center one do you want to put it on? The center one? So you want to do this. Okay, let's do it. Okay, so if we do that, let's check if it's V-shaped. So now we have to do VSEPR stuff. What is the electronic geometry of this right here? Electronic geometry. Not bad. Tetrahedral, there's 4 groups, and with 2 lone pairs, it's bent. Is that okay? So bent is the molecular geometry, so saying this will be bent. This one you'll notice doesn't even really exist in our VSEPR table, but that would make this structure looking something like this. That does not look like a V to me. Okay? So this cannot be the correct structure. Let's also double check what's the formal charge of that right there. Yeah, it's like -3. Yeah, that's not good. Okay, that's not good. What's the formal charge of that right there? +1. That's okay. So we don't have a good Lewis structure, especially because of that formal charge. Does that make sense? Does everybody know how to calculate formal charge? Okay. Okay. All right, I will trust you. So, try again. Let's go to right where we were. Here we were right there. Okay, where do I put those 4 electrons? No, I haven't even got to double bonds yet. I just want where to put what atoms to stick them on. Okay. What's the molecular geometry of the center atom? Bent, 2 lone pairs, 4 groups. What is the electronic geometry of this atom right here? Electronic. Trigonal, bipyramidal, 5 groups with 3 lone pairs. What do we call it? Linear. This one's identical, so it's also linear. Will this make a V? Yeah, this will definitely make a V. It'll be bent in the center and straight on the sides. Okay? This is our structure. But let's double check the formal charge, because formal charge is not good. We don't have a good structure. Again, what's the formal charge of this one right here? In the middle. +1. What's the formal charge of this one? Make sure by the test you can really do this. Okay. You don't have to be able to know it now, of course, but in about like 3 days. -1. What's the formal charge of the ends? Either end. Zeros. Okay. The sum of the formal charges equals overall charge. We're good. We got it. This is the final structure for I5 minus. Now let's do some of the other things. Let's do hybridization. What's the hybridization of this atom right here? This one right here. 5 groups, sp3d. Same with this one, sp3d. This one is sp3, 4 groups. Okay? Polar or non-polar for the ion itself. Polar or non-polar. It is definitely polar. Why? It forms a V shape. It's fully asymmetrical with its electron distribution. A V. There's no way a V or anything bent like that could be non-polar. Okay? All right. Is that? We did Vesper. We did. This has no resonance. That is of significance. This is a pretty good structure. You could probably mess around with some double bonds. Did you want another Lewis example, or are you satisfied? You want another one? No. Who does not want another Lewis structure? Wait, okay. Big hands. Who wants another Lewis structure? Okay, nobody. Okay. All right, so you're somebody, the 3 of you who raised your hand, but not enough for majority vote. Okay, next. Moving on down, shielding and Z effective. This is, I'm going to flip over to the reader because this will be easier to showing you the picture of the reader. Basically, what you need to know for all of these periodic trends, not just Z effective and shielding, is given 2 atoms, you should tell me which one has the higher or lower of the given quantity. So which one has a higher or lower radius, which has higher or lower whatever. So Z effective, you just need to know, goes along the row only. Z effective means it's the effective, Z itself is what? What's Z itself? It's the atomic number, really, and the effective nuclear charge. Those would be the same thing. So it's the atomic number. So say for carbon would be 6. But because there's core electrons, the valence electrons might not experience all 6 of those protons. Because they might not experience all 6 of the protons, it might be as effectively they're interacting with only 5 of the 6. That would be Z effective. And that's because the core electrons will block or shield the valence electrons from experiencing the full charge of the nucleus. So the full charge of the nucleus for carbon is 6. Because there's core electrons blocking that, the valence electrons might only experience 5 or 4 of the total 6. So Z effective is always equal to or less than the full Z. Okay, Z effective is always less than or equal to the full Z. It goes to the right. Screening and shielding are the opposite because screening and shielding, they go to the left and down, cause Z effective to go down. Okay, so the bigger they are, the smaller Z effective is. That's really all I have for that one, unless there was a question. Yeah. This is page 80 of my reader. Okay. Cool, that was easy. We will finish something. Okay, oh my gosh. Let's do quantum numbers. Yeah. It's a good place to start. And e-configs. Do I need to do more electron configurations? Who wants more? Sorry, man. You can ask me later, okay? All right. I guess I did enough with that nitrogen. That was a good combo problem. Okay. What was I doing? I was doing quantum numbers. So there's a couple ways that quantum numbers kind of rear their beautiful heads. One is, let's say we have a 4D m sub L equals -3. How's this orbital right now? It's impossible is how it is right now. N is what? L? Is this possible? Yeah, that's not possible. You can't have -3 because m sub L and L, or m sub L is bound by positive to negative L. So it'd be between 2 and -2. So -3 wouldn't be possible. So that's one type of question to ask you if something is allowable or possible. This one's not. It'd have to be like -1 would work, -2 plus 2, etc. Okay, another possibility. Let's say we said for 4D, how many nodes do we have? 3. Yeah, what kind of nodes are they? How many angular nodes and how many radial nodes? Do I need to explain that more? Is that okay? Wait, who needs more explanation on this one? Okay. Okay. Well, now everybody's excited to raise their hand. A 4D, or a D in general, looks like this. Okay, clover leaf. 4 petals. There's always 2 built-in nodes. This one and this one. Okay, those are built in. If they are planar like this, what do we call them, anybody? Yeah, those are angular. Planar nodes are angular. Okay? Nerds, being here don't tell your friends you're here at 8 a.m. in the morning. Okay, you will not be able to procreate. Okay? Radial nodes, the leftover nodes are always radial. So whatever does not get summed up by the angular nodes is always radial, and this would be it for this one. Okay? All right, this is also kind of wave functions. So somebody was asking me earlier, this is doubling as wave functions. You'd want to be able to either recognize and or draw the wave functions. So you know the S, the P's, and the D's. I think that's the main thing I would say. Here's an example of a T, none in particular. And I drew out the nodes. So for wave functions, be able to draw it, be able to label all the quantum numbers of it. So N, L, if given M sub L, usually not. And then be able to count the nodes and label the nodes if necessary. So that would be what I would encourage you to know for the wave function. Okay, let's see. What was it? It's quantum numbers. There's another type of question. Let's say you had, let's take carbon, 1s2. Oh, hey, here's another electron configuration for free. 2p2. Let's draw this kind of out with boxes. 1s2 2s, 2s2, and then 2p. So here's the electron configuration drawn out. 2p2. Another way you can get an electron configuration question, or not what was it? Quantum number question, is to label the quantum numbers of these electrons. So, for example, for the electron on the left, the first one, okay, first electron, I'll just call it 1. It's the first one there on the left. What's the quantum numbers? N, L, M sub L, and M sub S. What's N? 1. What's L? 0. So 1, 0 for S, M sub L. Has to be 0 for L, 0, M sub S. Plus 1/2 because it's pointed up. 2, let's do the next one over. What's N? Still 1, L is still 0 because it's a 1S. What's M sub L? If L is 0, M sub L must be 0. So let's get it from this. What's M sub S? Now it's negative 1/2 because it's the one pointing down. 3, let's do the third one, the one right here. What's N? 2 and 0 because 2S. 2S. What's M sub L? Must be 0 if L is 0. What's M sub S? Yeah, that one's pointed up, so it's a plus 1/2. Let's do the fourth one. Again, 2, 0 because it's 2S. 2S. 0 for S. What's M sub L? 0 because L is 0. And then what's the next number? It's negative 1/2 because it's pointed down. Should I keep going? Yeah, okay. Number 5, that one right there. Okay. What's N? 2L? 1, because it's 2P. M sub L. Oh, we'll skip it. We'll do it in a minute. Okay. What's M sub S? Okay, we'll do it after we do 6. Okay, number 6. Again, 2P. So 2, 1, and it's again pointed up. So plus 1/2. In this case, we didn't teach you in this class the correlation between the M sub L values and the 2P orbitals. So on finals, if you look through the keys, the ones we gave you, we'd accept any of the 3 possible quantum numbers for L equals 1. So plus 1, minus 1, or 0 would be accepted, though it is minus 1. Minus 1, and the next one is 0. It would actually be the actual answer, but any of the 3, minus 1, 0, or plus 1 would be accepted in these 2 spots. Okay. All right, I'm going to move on. Oh, yes. Question? Yes?
On one of the practice exams, there's a question saying, find the ground state of the single valence electron of copper. So how would I be able to find the quantum numbers for that?
The ground state for a single electron of copper. Ideally show me when we get to our specific questions. But it would depend which electron. It's all those electrons right there. But say if it's the 3s1 electron, then a 3 and a 0 and a 0 and then a plus 1/2. Yeah, but you can show me after if it's slightly differently worded. Okay, I'm going to go on. Yes, quickly.
I'm just curious, how did you determine M sub L? How did you know that it was negative 1 and 0?
Because I know. I mean, it goes in order. It counts from the lowest one to the highest one in the boxes. So minus 1, 0, plus 1. But you haven't learned that, so you can pretend I didn't say that. Yeah, but that's what it is. Is that okay? Yeah. All right. Oh, I did an orbital. Sweet. Okay. Let me do the root mean square. Okay. You are a mess. Is this. So the root mean square, it's going to be a simple calculation. So let's say we're at temperature is 207 degrees Celsius. And let's say, somebody pick an atom for me. No, iron could be
Oxygen.
Okay, oxygen. Okay, I'm taking oxygen. That's the first reasonable one I've heard. Okay. All right, so all you would do is say 3R is a 8.3145 joules per mole Kelvin. Has to be this one because you need the one that has SI units. Let's do the denominator. Oh, what's the temperature? Make sure to change the Kelvin. Like I add 273 to that number. Yeah, Kelvin, duh. I just picked a random number. So oxygen, 32 grams per mole. The problem is what? Yeah, the units, the grams. I need to change this to kilograms to be an SI unit. So 1 kilogram per 1,000 grams. So that kind of calculation. That's all I have on that one. Okay, that was a fast one. Let's do a redox, and I think. Oh yeah, I have a good one. We'll do redox is next. Give me a second to write it down here. Yes. Okay. All right. We're gonna bounce this with redox. Okay. So let's get our two half reactions going on. Let's also work on some charges. What's the oxygen? What's the charge on oxygen? Or I guess I should say oxidation state. 0 here. Both of these are -2. What's the oxidation state of hydrogen? +1. How about carbon here? +4. Okay, oxygen's -1 here. Each of the hydrogens is +1. So that makes carbon what? Ooh, this is complicated. Is it 2? I like that, but I don't know if it's right. It's carbon 2? -2? Yeah, that works better. Okay. Yeah. Okay, so what is oxidized? What is oxidized? Carbon. Carbon is oxidized. What is reduced? Oxygen is reduced. Either way you look at it. Okay? So our oxidation half reaction goes to what? What should I write in the product? Okay, CO2, anything else? Nope, that's it. The reduction, I'll put on the next page. And let's change colors for the reduction. What do I write in the reactants of the reduction? Oxygen. What do I write in the products? I'm not going to write anything, that's it. Okay, any questions on either of these before I go on? Because this is the key part. Should I explain either of these? Yes. Why don't I write water? You don't need to. You can. You're going to guess where it is. But you don't need to because this is added in step 2 of the 4 steps of balancing half reactions. Water is added to balance oxygen. So you don't need it. You can, but it's unnecessary. Okay? All right. I guess people are okay? So, if you didn't know, I always ignore water, H plus, and OH minus when it appears in the overall reaction. Water, H plus, and OH minus is always ignored. Okay. Alright, let's do it. Step 1, balance whatever is not oxygen or hydrogen. That's carbon by inspection. 2 carbons on each side. Step 2, balance the oxygens with water. So there's 4 oxygens here, there's 1 here. So I need 3 H2Os. Okay? And then step 3, balance the hydrogens. There's how many on the left-hand side? 12. So I have 12 H pluses on the right-hand side. Step 4, balance the hydrogens with electrons, or balance the charge with electrons. So I need 12 electrons. Okay, balance the 0 here, so I need the 0 on the right. Okay, next one. Do the one on the bottom. Step 1, balance whatever's not oxygen or hydrogen. That doesn't apply. Step 2, balance the oxygens with water. Need 2 waters. There, the water's back. Step 3, balance the hydrogens with water, with H+. So balance the hydrogens, there's 4 here. So I need 4 H+ on the left-hand side. And then step 4, balance the charge with electrons. It's 0 on the right and +4 here, +4 electrons. Okay, I'll pause again for a moment. Any questions before I continue? Okay, questions? This is the time to ask. Okay, what am I going to multiply the top and bottom reaction by? 1 and 3, because I want the electrons to cancel. They're my intermediate, and I want 12 on each side. So now, add this all up. Oh my God, C2H5OH plus 3H2O. I'm going to write all the reactants. Plus 3O2 plus 12H plus. That goes to 2CO2 plus 12H plus 6H2O. Hopefully I did not miss anything. Let's try to cancel stuff. The H pluses all cancel on each side. 3 of the waters are gone, making 3 on the right. And we're left with, after the simplification, C2H5OH plus 3O2 goes to 2CO2 plus 3H2O. Okay, cool. Is this acidic or basic acid? Well, if it's acidic, how do I change it to basic? I could add H plus, OHs for every H plus, but there are none. So it's kind of, it's sort of a neutral answer. Yeah? You have to write the states. That is a great question. On the final, sometimes it's specified. In that case, you need to do so. This one you wouldn't, oh, you probably know. If you're in a frat, what's this? Maybe not your frat, okay? Maybe just my frat. If you're a human, what would this be? Okay? Cool. Good. Yeah. Read the question carefully on the final. Okay. Last question. We're going to move on. Say it. Oh, that's a great question. What is this? Acid, base, neutral, etc. What is it? This is acidic. It's acidic. Yeah, alcohol is acidic. It would only be a base if it's a metal with a hydroxide. A non-metal with an OH, it's no longer, sometimes it's called a hydroxide, but it's actually acidic when it's a non-metal. Yeah, and you'll learn why in 2B, beyond our scope of this class. But that was on one of the practice finals somewhere. Okay. Yeah, hi. The overall reaction is the final answer. She's asking what's the overall reaction. That was the final answer when you sum up both half reactions. You'll have to show me. Yeah, you can show me after. I can do wavelength right now. It's the length of a wave. Wow, are people into like super dark stuff? Okay. Is that all we need for the wavelength? Okay, cool. I mean, you can use this H over mu if it's de Broglie. If they give you a velocity, use this formula, the de Broglie, and you can find the wavelength from a particulate. That's definite. Or you know this equals lambda nu, or you can know that each equals hc over lambda. So there's a couple wavelength possibilities in calculations if you need them, but these are given formulas, so just look on the back. Okay, net ionic, next. Okay, I probably only have, oh, maybe I should ask you. I'm going to do like 1 or 2 more subjects. Is there a preference on what I do? I don't have to do net ionic. Okay, you get to raise your hand. You can only vote twice. Who wants Dalton's law? Okay. Who wants net ionic? Oh my gosh. Okay, nobody cares. Who wants hydrates? Oh, you guys like hydrates. Titrations. Okay. Combustion. No. Limiting. Ooh, close. Percent composition. Okay. So it's between these 3. This one, this one, this one. Vote for the one you hate. Limiting the one you don't want. Limiting reagents. Oh gosh. Titrations. Who doesn't want this? God. Who doesn't want this? Yeah. So close. Alright, I'll cut this one. I don't know. I have to pick one random. Okay. So we're gonna do hydrates and titration. Let's do titration first. Okay, this would be a typical titration reaction. You want to be able to write the products in balance, so it would be water plus the salt, or in this case a neutralization reaction. And then you want to balance, so this should be 2. And then this would be 2. I think that does it. Typical kind of question gives you the molarity of one, and say its volume. And then it can ask you a number of things about the other. Let's just find the mass. So there, it could ask you the mass, it could ask you the moles, it could ask you the molarity, a lot of different possibilities for the second. What we're going to do is go like this, change this to moles, use a molar ratio to go to moles of this one, and then go to what they asked for. So a 3-step process. Step 1, go to moles. So 100 milliliters of the initial. Change that to liters, 1,000 milliliters per liter, and then now we've got 1.0 moles per liter, or molarity, 1 molar. This all changes to, now we've got moles of the strontium hydroxide. Step 2 is to go to moles of the one we want. So in this case it's 2 moles of HCl for every 1 mole of the strontium hydroxide. Okay? Now, so we completed step 2. Now, we're at moles of the one we want, in this case HCl. Now we just need to take our last step, which is use the molar mass, in this case, to get to what we want. In this case, molar mass would be 36.45 from 3 electrons. Okay? That would be a pretty typical titration question. In and of itself, the titration questions would be always following this format, especially when they're not comboed with other questions. Okay, the second thing you wanted me to do, and the last thing, hydrates. Hydrates are basically just, let's say, cobalt chloride are these. So all of these are with a dot in between. This means that the water is loosely bonded in some way or another to this cobalt complex. So that would be cobalt 2 chloride. And then this is, you name this with the same prefix as moleculars. That's page 22 of the reader. Molecular prefix is right here. 22 of the reader. Okay, hexa in our case. Hexa, and then the water is always named hydrate. Always named hydrate. This is the prefix for the number 6. Okay? So you can almost do unlimited problems with them because you can find them in reactions, you can find them in all kinds of possible, you can find the molarity of it. It's just a molecule. Okay? It's just a molecule like any other molecule. You just need to know this dot just means that there's another 12 H's and 6 hydrogens in the molecule. Okay? And they're all in the water form. Alright, that's all I have about hydrates. Cool. Well, I hope you enjoyed it. For those who are going to take off, good luck on the final. Take care. And in about 2 minutes, we're going to resume with specific questions.